So 98.9% of all of the carbon on Earth has 6 protons and 6 neutrons. And so each proton and neutron weighs 1 atomic mass unit. So you'd add these up, and 98.9% of all the carbon on Earth weighs 12 AMU, or atomic mass units. On the other hand, you have around 1.1% of all the carbon on Earth also has 6 protons. It has to have 6 protons in order to be carbon. Having 6 protons in a nucleus is what makes something carbon. But instead of 6 neutrons, it has 7 neutrons. And so the overall mass of the carbon atom will be 6 plus 7, or 13 AMU. So almost all of the carbon on Earth has a mass of 12 AMU, but a small percentage has 13 AMU. This is a small number, but although keep in mind, if you have a gigantic number of atoms, like 1 trillion atoms, 1.1% of that is a lot of atoms, even if it's relatively small compared to the amount of other types of atoms. Okay, so what does that mean? That means if you have a methane molecule, the mass of it is going to be the mass of the carbon plus the mass of the 4 hydrogens. Well, 98% of the time, you'll have carbon 12. This carbon will be carbon 12. And so the mass of this methane molecule will be the 12 from carbon plus the 4, 1 from each of the hydrogens. So the mass of this would be 16 AMU. And you would get a peak, percent relative abundance on the y-axis. So, and you would get a peak at 16 AMU on the mass spectrum. It would be the molecular ion peak. 1.1% of the time, that carbon will not be carbon 12, it will be carbon 13. And so the mass of the methane molecule will be the mass of the carbon, which is 13, plus 4, 1 from each of the hydrogens, or 17 AMU. Now, remember that the height of these peaks, the height of those peaks tells you how often you got that fragment. Well, if the molecular ion peak at 16 is a certain height, then the peak 1 mass unit above it is going to be 1.1% as high, because you'll only get this carbon 13 1.1% of the time. So the peak that represents molecules that have it, that'll only be 1.1% as high, because it doesn't appear as often. This peak is a new peak. It's the molecular ion peak, so that symbol like we had before, capital M because it gives you the molecular mass of the compound. We have the positive charge because it has a positive charge because an electron was locked out, and we have the dot to represent that it's a radical, that there's an unpaired electron in the molecule. So the molecular ion peak, but it has a mass that's 1 higher, so it's called the M+1 peak. Okay, so that happens if you have methane. In the case of methane, that would happen 1.1% of the time. So now imagine what would happen in 3 different scenarios. So let's take what we had with methane. Let's compare that to what would happen in ethane and what would happen in propane. Now in methane, we said however high, so we have the mass on the x-axis, the percent relative abundance on the y-axis. We said in methane, however high the molecular ion peak is, the M+1 peak will be 1.1% as high. Because the carbon that's giving it that extra mass only appears 1.1% of the time. So this peak here is 1.1% as high as the molecular ion peak. Okay, imagine you have ethane. In ethane, you have carbons, but each of those carbons could have a carbon-13. In other words, because you have twice as many carbons, a carbon-13 will appear twice as often. And so the M+1 peak will be twice as high. It will be 2.2% the height of the molecular ion peak. And if you had propane, propane has 1, 2, 3 places where carbon-13 could appear. Carbon-13 is 3 times as likely to appear in propane as it is to appear in methane. So it'll appear 3.3% as often as the molecular ion peak. So this M+1 peak will be 3.3% of it. It'll get higher. In other words, for every carbon you have in a molecule, the M+1 peak will go up by 1.1%. If you have 1 carbon, it'll be 1.1% the height of the molecular ion peak. If you have 2 carbons, it'll be 2.2% as high as the molecular ion peak. If you have 3 carbons, it'll be 3.3% as high as the molecular ion peak. So whatever percent it is of the molecular ion peak, just divide that by 1.1 and you have the number of carbons. 1.1 divided by 1.1, 1 carbon. 2.2 divided by 2.2 divided by 1.1, excuse me, 2 carbons. 3.3 divided by 1.1, 3 carbons. All right. Well, if you have a random peak, how can you get these percentage values? To find a percent is a part over a whole times 100. The part that we're interested in is the M+1 peak. We want to know how big that is relative to the whole molecular ion peak. So we're going to take the size of the M+1 peak divided by the bigger peak, the molecular ion peak, and multiply by 100. And that will give us these percents that we have down here. And notice what we did with those percents is we divided them by 1.1, and that gave us the number of carbons. Divided by 1.1, that's the number of carbons. Divided by 1.1, that's the number of carbons. So if you take this whole thing, and you divide that by 1.1, that gives you the number of carbons in a molecule. So we've derived this little formula here. And this formula is really useful because we can use it to start to build a possible molecular formula. That is what is trying to happen, what they're asking you to do in this exercise 1521. So the question says, propose a molecular formula for a compound that exhibits the following peaks in its mass spectrum. And notice they're talking about two things. They're talking about the molecular ion, and they're talking about the M+1 peak. Well, all we have to do is use this formula. Oops. All we have to do is use this formula to get the number of carbons. The first thing we have to do is to figure out the percentage, how high is this M+1 peak relative to the molecular ion peak. And they give us percents here. Those are the percents that we want to plug in to the formula. Notice that the M+1 peak is not 1.7% of the molecular ion peak. It's 1.17% of the highest peak, which is the base peak. Remember, in a mass spectrum, the peak that gives you the molecular mass is the molecular ion peak. But the highest peak, the peak that represents the most stable molecule that made it to the detector, that made it there most frequently, that's the base peak. By convention, the base peak is assigned a value of 100%, and the heights of everything else are compared to that. So in this example, the molecular ion peak is around 40% the height of the base peak. And the M+1 peak is around 1.7% as high as the base peak. But we're interested in how high this M+1 peak is relative to the molecular ion peak. And that's why we're taking this percentage here. All right, so we plug everything in. We say, fine. The percentage they give me for the M+1 peak is 1.7. So I'm going to plug that in. The percentage they give me for the molecular ion peak, is 38.3. So I'll plug that in. And then I'm going to multiply by 100. That'll give me the relative height of the M+1 peak to the molecular ion peak. Once you have that relative height, 1.1, well, okay, let's just get the relative height there. So 1.7 divided by 38.3 times 100 is giving me around 4.4. So that's 4.4. Every 1.1% of that is coming from the chance of a carbon-13 appearing in place of a carbon-12. Every 1.1% of that is coming from an individual carbon. So we can get the number of carbons by dividing that by 1.1. So 4.4 divided by 1.1 is 4, and so we have 4 carbons in this molecule. Okay, so let's set this work aside. We've done the first part. Now we know we have 4 carbons. So now we know we have 4 carbons. But what they're asking for here is a possible molecular formula. It may not be the correct molecular formula, but it's a plausible one. Well, we know for a fact that there have to be 4 carbons in a molecule. Now let's think about how we can add hydrogens, or the other 2 most common elements in a molecule, oxygen and nitrogen, in order to get a plausible molecular formula. The first thing you want to think about is the maximum number of the maximum number of hydrogens that could be in a molecule. Think about any carbon chain. However many carbons you would have twice as many hydrogens going up and down, and on the ends, you would have 2 more hydrogens. So if every carbon has all single bonds, and you're stuffing a carbon chain with as many bonds as you can, with as many hydrogens as you can, you would have twice as many, the most hydrogens the molecule could carry is twice as many carbons, plus 2. Twice as many carbons because each carbon has bonds on top and on bottom, twice as many. Right? And plus the 2 hydrogens because the ends have those 2, the end of the chain has those 2 hydrogens. So the maximum number of hydrogens is 2 times the number of carbons plus 2. So in this one, the maximum number of hydrogens we could have, that would be 2 times the number of carbons, so that's 4, plus 2, that's 8 plus 2, that's 10. We could have 10 hydrogens max. Okay, so let's see where we're at. Because the molecular ion peak occurs at a mass of 72, the molecule needs a mass of 72 AMU. We have 4 carbons. So we know carbon is in the molecule. We have 4 of them. We know each carbon would weigh around 12. So that's 4 times 12, which would be 48 AMU coming from the carbons. If all we had was hydrogen, we could have 10 hydrogens max. Each hydrogen weighs 1, so that's 10 AMU coming from hydrogens, and we would only have 58 AMU. So we're far short of the number we need. So this molecule can't have just hydrogens in it. It has to have something else. Now the 2 other elements that are most common in organic chemistry are nitrogen and oxygen. Let's take a second to think about how those could impact the mass, the molecular mass. And let's go back to our little carbon chain that we had a second ago, that we were using to think about the maximum number of hydrogens. So notice, notice that carbon has an even molecular weight, 12 AMU, and it's an even number. And notice that there's an even number of hydrogens here. 2 on the top and bottom of each carbon, and then 2 on the ends. So a hydrocarbon with all single bonds should have an even molecular weight. What happens when you add a nitrogen? When you add a nitrogen, the end of the molecule now doesn't have 2 hydrogens, it has 3. And so the molecular weight becomes odd. If a molecule has an odd number of nitrogens, the molecular weight will be odd. Here, the molecular weight is even. And so, this molecule cannot have an odd number of nitrogens. So, because we could only add 1 nitrogen here, it would not have a nitrogen. So remember that rule, it's called the nitrogen rule. If you have an odd number of nitrogens, then the molecular weight is odd. So, since you don't have any nitrogens, you'd go to oxygens. You'd assume you'd only have one, because if you had more than one, it would take you above your molecular mass. Each oxygen weighs 16. And if you added 2, that would be 32. That would 32 plus 48 is 80. So that's above our mass. So we can only add one oxygen, and so that gives us 16 AMU from oxygen. So now, at this point, we have 48 plus 16. That's 64. So this is 64. And so how many hydrogens would we need to add to get that up to 72? We'd have to add 8, because each hydrogen is 1. So that would give us 8 AMU. And so if you add all of that together, you should get 72 AMU. 48 plus 16 plus 8 is 72. So a plausible molecular formula for this, it may not be the right one, but a plausible one is C4. That much we know has to be the case. O, that could be the case. And then H8. So 4 carbons. 1 oxygen, and 8 hydrogens would give us a mass that adds up to the one given for the molecular ion peak. So to recap, what we did was we used this formula to figure out the number of carbons. We took the percent they gave us for the M+1 peak, divided it by the percent they gave us for the molecular ion peak, multiplied it by 100, and that gave us the relative height of this to this. Then we divided that by 1.1, because every 1.1 of this percent was coming from 1 carbon, so this gives us the number of carbons. Once we add the number of carbons, we saw if we could add the maximum number of hydrogens. We saw if we could add hydrogens to give us the molecular mass. There's a cap, though, at the number of hydrogens you can add. So that didn't get us to the right mass, so we started to add either nitrogen or oxygen. We couldn't add nitrogen because an odd number of nitrogens would give you an odd molecular mass, and the molecular mass here is even. So we added oxygen. And once we did that, we saw what weight that got us and just added hydrogens until we had the molecular mass we wanted. So we'll do this again several times in this problem, but I'm going to make separate videos for those so that each video isn't unduly long.